All right. Well, good afternoon, everyone. I am Lisa Bronner, and we are starting a new series of Facebook Lives for the Going Green Facebook page. And this is a series of experiments. Now, I won't get started on our topic until 1, but I just wanted to tune in a little bit early in case those of you who joined early, you know you're in the right spot. So today we're going to start with our first session. We're going to look at surface tension. If you haven't had a chance yet to gather the supplies, it's not too late if you want to join in. You probably have some of these things handy. And if you haven't grabbed your kids yet, grab them too, because they might enjoy these experiments. And this is great for kids to learn some chemistry, good for adults to learn some chemistry. And also, you're going to learn how soap works, why it is still the recommended way of cleaning many things, even though it's, well, old. So we'll start in about 3 or 4 minutes. However, I received a question from a young friend of mine about soap. If you saw some of my promo posts for this live, you saw that I mentioned that this soap is very old, and how can something that is that old still be the recommended way that we clean things, especially nowadays? I mean, we certainly have been hearing a whole lot about soap in recent months and the need to wash our hands and to wash surfaces, and that soap really is adequate, more than adequate, at getting things clean. So the history of soap, and realize this is some of that really archaic knowledge that I've got in my head. The history of soap is thousands of years old, because soap was a bit of an accidental discovery that some very observant person noticed. So soap was originally discovered by observing cooking pots and ashes. And the most fundamental way you can make soap is out of fat from cooking and ashes from the fire. So if you can picture, a pot over a fire, and they've got something bubbling in the pot, and it's got some grease floating on top, and the grease falls over the side and drips down into ashes. So ashes is an alkaline, and the soap or the oil is a fat, and that is the basic reaction of soap. You have that oil reacts with the ashes and forms soap. And probably the next thing they observed is that maybe it rained and this soap would run down, and all of a sudden there'd be these like clean streaks on the rocks. And how did that happen? And somebody realized that it's because this reaction between the oil and the ashes is creating soap, and then it's running down and cleaning as it does. So that was the first soap, was in the cooking fires and realizing it happened. And so the first soap ever made was probably with animal fats and then the super basic ash. Now, we've refined that a lot, and we've realized that not just animal fat can make soap. You can also use any oil, any vegetable oil, coconut, olive, like we do at Dr. Bronner's, or you can even use synthetic or petrochemical oils and that sort of thing to make detergents and non-soap cleaners, but they have the same properties. So we've refined it. It's not only animal fat. We also know that you don't have to burn a fire and use the cooking ashes. You can just use any super strong alkali. Sodium hydroxide, which is commonly called lye, has been used for centuries, and literally you boil it up, and after a while the reaction happens, and instead of oil and alkali you have soap. So there's the history of soap. Soap is really old. It's not a new thing, but there really is nothing that matches it for its efficiency, effectiveness, and safety. So I spend my life working with soap. I think it's absolutely fascinating. There are parts of soap that are unlike any other molecule, and there's a lot to learn there. So that's the purpose of this next series of Facebook Lives, 3 sessions looking at the properties of soap with some pretty cool experiments. So it's 1 o'clock now, so I'm going to start with our Facebook Live officially. If you're just joining us, I am Lisa Bronner, and I write the blog Going Green with a Bronner Mom. I also run this Facebook page, the Going Green Facebook page, to help people make transitions to a healthier lifestyle, to bring lower toxicity into our homes, and also to dial back our whole lifestyle so that we can live simpler, more peaceful lives. I also happen to be the granddaughter of Dr. Bronner, who founded the company Dr. Bronner's that makes organic personal care products, and my family still runs that to this day. So we all do our little part. Now, I wanted to do this particular series called Experiments in Soap, looking at the characteristics of soap, primarily because I think it's really cool. And secondly, because it's summertime and maybe you need some things to do, or the kids need some things to do, and these experiments are easy to do at home and they're pretty nifty. And thirdly, for adults, it's because I want you to know that these cleaners that we recommend that are safe are also very effective. So 3 reasons that I thought about doing this series. But really that first one, because I think this is really neat, that's the main reason. So today we're going to look at the first ability of soap, which is breaking surface tension. Now, soap has an effect on water that is key to cleaning. So surface tension is something that many liquids can have. And like it sounds, it's something on the surface of a liquid that causes tension. So for an example of that, I'm going to talk about a balloon. So you guys familiar with balloons? When they're blown up, they're pretty tense. I could squeeze it a little bit, but we all know what will happen if I squeeze it too much, because the surface tension can only take so much. Now, another way to think of surface tension, you could think of it like a balloon, like a skin over water or a skin over a liquid. You can also think about it like a bunch of friends, holding hands, and everybody's holding hands and everyone's leaning back and it's all fun until one person lets go. And that's when surface tension breaks. One person lets go and everybody falls. Now, as you might expect, the same holds true for a balloon. So a balloon is tension. There are a bunch of molecules on this balloon and they're all holding onto each other, and that's why this balloon is blown up. But what happens if I take a pin and this tiny point makes a tiny break in the surface tension of this balloon? I bet you know what's going to happen. It's gone. One tiny break in the surface tension and the whole tension fell apart. Well, that is the effect that soap has on water. Because even though we can't see it, soap has surface tension too. I'm sorry, soap does have surface tension too, but what I meant to say is that water has surface tension. And the surface tension of water keeps water from doing a super job cleaning. Water can do an okay job cleaning, you rinse something, but it can't do a super job cleaning because of its surface tension. We all know surface tension because we've all done a belly flop into water, and as soon as you hit that water, it hurts. Now, what is it that hurts? It's a surface tension. The water's actually holding on to each other, and it doesn't want you to break through. So when you pour water into a plate, which is what we're going to do, and if you are doing this along with me, go ahead and pour water into the plate. You may not be able to see it, but there is tension on this water. And unlike with the balloon and the pin, I can't actually break it just by poking it with a physical thing. I can't punch it. I can go through it, but I can't break the surface tension. The surface tension will just stay all around like my pin, or even if I put my finger in it. I didn't break the surface tension. The surface tension of water is chemical. It's actually an attraction. And so I actually have to break that attraction. Now, another way to demonstrate that there's surface tension here is by sprinkling something really lightweight on top. Now, I've chosen oregano here, partially because I have it, partially because it's a really lightweight thing. So I have oregano here floating on my plate. It's floating for 2 reasons. One is because it is lightweight, and the second reason is because of the surface tension. You could use pepper, you could use any herb that's floating on there. And we all know that there are insects that use surface tension to walk across water. So I've got the oregano floating right there, and you can tell that it's right up on top. I can actually see the shadow of the oregano on the bottom of my plate. So if you're going to do this along with me, get to this point. Fill your plate with water and sprinkle your oregano on top. And then we're going to break it. But I can't do it with a pin. It's not going to work because this is not a mechanical thing. It's a chemical thing. But I can do it with soap. Now I have here just Dr. Bronner's Castile soap. Happens to be the eucalyptus. Smells really woodsy here. And what I'm going to do is I'm going to take a Q-tip, and I'm going to dip it in the soap. And before I touch it to the water, I'm going to have the camera zoom in here. I have my son helping me here with the video work today, since we're all at home. I don't have my usual work crew, so he's going to zoom in here on my plate so you guys can see this happen. And I will wait till he gives me the go-ahead that we are zoomed and ready. So I have just dipped my Q-tip in the soap. That's all we need to do. All right, now I'm going to touch this, just touch it to the middle of this, and I want you to see what happens. Ooh, I didn't make a wave. I didn't touch it that much, but you saw the oregano fly to the rim. What happened there is that the soap popped the surface tension, and just like a balloon, the whole thing fell apart. So let me show you something else before we zoom back out. What happens if I put more oregano on here? Now it's going to float just because oregano is really lightweight. However, I'm going to show you that there's actually no surface tension left, because if I do this again, the oregano doesn't move. You can only pop a balloon once. I can't pop that surface tension again. So go ahead and zoom back out there, buddy. Now, I can't do that again with the same plate because it's already been popped. But as I mentioned, there are other things with surface tension, and there are other things that can break it. So we're going to do a little experiment. Now, one thing I forgot to mention at the beginning is that I have several people helping me here today that you can't see. Number one is my son, who's running the camera. My cousin is also ready and waiting to answer your questions in the comments. So if you have any questions about soap, or you have a question about me or the experiment or whatever, my cousin Daniel Bronner, who's just graduated from college with a degree in chemistry and math, he is ready and waiting to answer your questions, so feel free to write them out. Even if a kiddo has a question, put it there, or you can pretend you're a kiddo if you feel shy about asking a simple question. Go ahead and put your questions in the comments. I might even do a few of them here on the live. But either way, your question will be answered. Daniel is waiting. So what I'm going to do, now what I just did for you was a demonstration. It was not an experiment. The reason it wasn't an experiment is because I knew exactly what was going to happen, partially because I've done it before. The difference between a demonstration and an experiment is asking a question. An experiment is when you ask a question that you do not know the answer to. So I'm going to ask a question. My question is, what else will break surface tension? Now I'm going to fill these 4 plates with soap. I'm so sorry, I keep making that mistake. I'm going to fill these 4 plates with water, and I'm going to sprinkle oregano on all 4. And then we're going to see what other random liquids can break the surface tension. So I'm going to put some oregano on it. Let me tell you, this is making me want some yummy Italian food because this oregano smells so good. All right, so we've got oregano on all of them. If you could tilt the camera a little bit down so that everyone can see my 4 plates. All right, we already know what happened with the soap. That popped the surface tension. The second thing I'm going to use here is, actually I'm not going to use the salsas yet. I'm going to use olive oil, all right? Just a liquid I have in my kitchen here. What happens if I use olive oil? And whatever liquid you have, you don't have to have olive oil. All right, so another Q-tip. So right here, I'm going to put the Q-tip in, and let's see if it has any effect on the surface tension. Does it make the oregano move? Not a bit. Doesn't move at all. So therefore, you know that olive oil is not effective at breaking surface tension. Couple more things I have. In this dish, you can't even see it here, but in this dish is shampoo. All right, so shampoo is this effective at breaking surface tension? I'm going to take another Q-tip here and touch it here. Ooh, a little bit. It's definitely not as fast as the soap, but it's still moving, right? It's still moving, kind of taking its sweet time. Okay, it seems to have stopped. So it did a little bit more. Okay, all right, so shampoo. Shampoo works. There's something about shampoo that breaks surface tension. A couple other things I found in my kitchen. Soy sauce. Let's see. Does soy sauce break surface tension? Nope, not a bit. Not a bit. I'd love to hear what you're trying this with, so go ahead and put what you're finding in the comments. What are you using, and did it break the surface tension? I would love to hear some of that. So, what do I have here? I have ketchup, okay? Literally, I opened my fridge and found some things. Ketchup. Nope, ketchup's not going to break surface tension. In fact, this is interesting. I don't know why this is happening. The oregano seems to be attracted to the ketchup. Wow. Huh. Well, that's an experiment for another day. All right, so we learned some things there. Go ahead and back up to show my face, buddy. Thanks. All right, so we found that soap and shampoo were two things that affected the surface tension, and that olive oil, ketchup, and soy sauce did not. So what do we do with that? So what we found is that soap and shampoo have a similarity, and the fancy word is they're called surfactants. They're called surfactants. They are surface active agents. Can you hear the word surfactant? Surface active agent. Surfactant. They affect the surface tension. The reason this is important is because on its own, water does not want to go down onto surfaces. Water wants to stay touching water. And when you're trying to wash something, that can be really frustrating. You might have tried to wash your hair with just water and the water's like bouncing off of it. Soap breaks that so water will penetrate. In a sense, soap makes water wetter. It makes water wetter so that the water can get down to the surface and actually clean it. So, now as I told you before, we cannot do the experiment twice because with the same plate because it just won't work. So I'm going to clear these out. And what are we going to do with this information? As I said, if you have any questions about what we just did there, feel free to put them in the comments. Alrighty, so now I promised you something else. I promised you that we were going to power some boats with soap. And that might have sounded a little funny. You know, Dr. Bronner's is kind of a green company, so are we talking about a new way of fueling our vehicles? Not really. This will not work for that purpose, but it's still kind of neat anyways. So we're going to do another experiment involving surface tension and soap. So I suggested you have a baking pan because I wanted something long. This is a small griddle of mine. I'm going to fill it with water. And if you did not do the setup, you don't have this in front of you, this video is going to be available afterwards, and you can go back and watch it and do the experiments then. All right, so just plain water here, and then I have some pretty nifty little boats. They do not need to be this fancy. These were just made out of cardstock. Now we're going to do, again, another experiment. What is the difference between an experiment and a demonstration? An experiment means you ask a question you don't know the answer to. So a moment ago, you might have seen that I pulled over my Salsuds. Salsuds is another product that Dr. Bronner's makes. It's actually a detergent, and I have our soap. You noticed a moment ago with the shampoo that it worked, but it didn't work as fast as the soap. The soap was like, the oregano flew. The shampoo made the oregano kind of slowly drift. What I want to find out is which one of these is going to break the surface tension faster. And the way that we're going to find that out is by racing some boats. So Nate's going to zoom in here on my setup, and I'm going to put my boats right here. I don't want to put them in the water yet because I don't want them to take off without me. I'm going to get 2 new Q-tips. You got to get new Q-tips because if it's got something else on it, it won't work. And as I said before, you can only do this once. So the green one is going to have the soap. So there's the green one, and the blue one is going to have the salsids. Okay, I'm going to put my or my boats at their starting line. Oop, 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 stay there. Stay there. Okay, I've got my soap and oh my goodness. Wow, the soap still worked better. Honestly, I'm surprised. The reason I'm surprised, now it could be that that blue one turned, but the soap did seem to work faster at breaking the surface tension. I'm a little surprised because salsids is actually more concentrated than the soap. So my guess would have been that the soap would have worked slower than the salsids, but that's not what happened. Okay, Nate, go ahead and tilt back up to me here. Okay, so what we just found out there is that soap, the Castile soap actually broke the surface tension seemingly faster than the salsids did on my snazzy little green boat here. Now, in order to get a true result, we should do this a few more times. But as I said, I can't do it again here because I've already touched soap to this water and the surface tension is gone. So if I want to redo the experiment, I have to go rinse everything off. I even have to rinse my boats off, and I actually lacquered these so that they wouldn't get waterlogged. And then I could redo the experiment and see what happens. So that's a couple different ways that you can see surface tension breaking. You can see it with the oregano. You can see it here. It actually moves the boat across the water, and that's just an evidence of something we can't see. We can't see the surface tension on its own. It can't see the skin on the water, but you know that it was there, and you know that now it is not there. And just to show you again, if I tried to race the boat again, it's not going to move just because there's no more surface tension to break. So those are my few demonstrations and experiments with surface tension. Next week we're going to look at another feature of soap, and honestly, next week I'm even more excited about for two reasons. First of all, surface tension breaking is important, but what's even more important that soap can do is that it is the great peacemaker between oil and water. It makes oil and water, which naturally want to repel, it actually bonds them together. And that's what next week's experiment is going to show. Now, I call next week's experiment kaleidoscopic soap because we're going to show this mixing of oil and water using food coloring, and it makes an absolutely mesmerizing experiment. I even recommend you have your own camera ready to take a video of it because it's just so fascinating to watch. So thank you for joining me for our very first session of experiments in soap. If anybody has any questions, feel free to send them to me. You can even put them on the comments later. I will check those, and my cousin Daniel will be checking them so that we can give you good scientific answers for what is going on with soap. So I'll see you next week for kaleidoscopic soap. Thanks so much.